The original 2017 transformer architecture was a theoretical breakthrough, but deploying it directly at today's production scale causes it to hit a physical wall. The vanilla architecture carries two severe computational flaws. First, its self-attention mechanism creates an O of n squared compute bottleneck, meaning processing costs explode exponentially as sequences get longer. Second, it optimizes purely for pattern completion, resulting in highly unpredictable hallucinatory outputs. This structural comparison highlights the shift. On the left is the 2017 monolith. To fix its inherent flaws, the industry had to abandon it. On the right is a modern 2025 production stack, a composite system requiring heavy interventions at the architectural, training, and deployment levels. That schematic on the right is our roadmap. To understand how a language model actually becomes steerable and deployable, we have to reverse engineer exactly what goes into those empty slots. The very first requirement is overhauling the base engine itself. The model must be able to handle massive parameter scaling without completely exhausting the hardware compute budget. Deploying a modern language model requires engineering a multi-stage pipeline designed to contain, optimize, and guide a raw statistical engine. This chart illustrates the pre-2022 scaling approach. The industry assumption was that increasing the model's parameter count, while keeping the training data largely static at around 300 billion tokens, was the best way to gain performance. The DeepMind Chinchilla paper proved those early models were massively undertrained. For a fixed compute budget, there is an optimal balance. If you double the parameters, you have to double the tokens, locking in a roughly 1:20 ratio. This meant previous scaling methods were wasting vast amounts of computational power. But even with an optimized data ratio, standard dense transformers force every single token through every single parameter. As models approach 1 trillion parameters, this creates a hard hardware ceiling. The architectural solution to that ceiling is a mixture of experts, or MOE. Instead of one massive feed-forward block, the layer divides into multiple specialized pathways. When a token enters the layer, a routing network calculates which experts are most relevant and activates only those specific paths. The model scales its total capacity to trillions of parameters, but the active compute cost per token remains equivalent to a fraction of that size. Over time, these pathways specialize. One expert handles syntax, another resolves rare vocabulary, a third focuses on numeric reasoning, with the router dynamically directing each token to the right node. By combining the data efficiency of Chinchilla scaling with the sparse activation of an MOE architecture, engineers decouple a model's total intelligence from its raw inference cost. Once the model is scaled, it still needs to process sequence order. Early transformers attached static tags to each token to indicate position, but this rigid approach fails when sequences extend past the length seen during training. Rotary positional embeddings, or ROPE, map positions mathematically. By rotating each token's query and key vectors by an angle dependent on its sequence position, the model can determine how far apart two tokens are simply by comparing their angles. It encodes relative distance instead of relying on a fixed tag. With position solved, the system hits another wall during inference. Generating text auto-regressively means the model must recalculate attention for the entire prior sequence just to predict the very next word. To eliminate this redundant calculation, engineers implement a KV cache. As tokens are processed, their keys and values are saved into a dedicated memory buffer. When a new token arrives at the layer, the system only calculates the keys and values for that single new input. It then pulls the historical data directly from the cache, turning an exponential calculation into a fast, linear path. Without the dynamic positioning of ROPE and the memory efficiency of the KV cache, processing full codebases or generating long-form documents would be too slow and rigid to exist in production. After structural optimization, the base model understands grammar and facts, but because pre-training only optimizes for next token prediction, it acts as a chaotic engine rather than an obedient assistant. The first alignment phase is supervised fine-tuning. Engineers apply cross-entropy loss to curated sets of prompts and human-written responses, forcing the model to adopt a structured conversational format. However, supervised fine-tuning only teaches imitation. To optimize the network for deeper, latent human preferences, like safety, tone, and conciseness, the system requires a mathematical scoring mechanism. This chart explains the transition from preference to reward. First, human raters compare outputs, creating preference data. This data trains a separate, dedicated reward model. As shown in the diagram, the reward model learns to analyze a single response and convert those relative human preferences into an absolute scalar score. That scalar score allows engineers to apply reinforcement learning from human feedback using an algorithm called proximal policy optimization, or PPO. The process forms a continuous loop. The main language model generates an output, the reward model assigns it a score, and PPO updates the language model's internal weights to maximize the probability of achieving a higher score on the next iteration. Crucially, a KL divergence penalty runs simultaneously inside this loop. This mathematical constraint tethers the network to its fine-tuned baseline. It prevents the model from hacking the reward system by generating bizarre outputs that technically satisfy the scoring criteria. Through this triad of fine-tuning, reward modeling, and reinforcement learning, the model stops blindly imitating text. It begins mathematically optimizing for the precise behaviors humans value. Relying on thousands of human raters to generate preference pairs creates a massive bottleneck. It is slow, highly subjective, and difficult to scale across nuanced behaviors. To bypass this limitation, Anthropic introduced constitutional AI. This methodology removes the human from the loop, replacing subjective preference data with model-guided self-improvement. The process relies on providing the model with a static rulebook, or constitution. The model generates an initial answer, but then critically evaluates its own output against those written principles. If it detects a violation, it revises the text until it passes the filter cleanly. The system then moves to preference training. It automatically compares two responses and determines which one better adheres to the Constitution. This generates vast amounts of alignment data instantly, completely removing the human judge from the reward modeling loop. By translating subjective human judgments into an explicit, programmable set of rules, engineers can rapidly and cheaply reshape a model's foundational behavior. Even with strict alignment, LLMs remain statistical generators. Because they are trained to optimize for linguistic coherence rather than factual truth, they will confidently hallucinate when operating outside their training distribution. This sequence flow outlines Retrieval-Augmented Generation, or RAG. It establishes a strict engineering boundary to ground the model in external reality. When a query arrives, a retriever extracts verified documents from a database and binds them directly to the prompt. The prompt includes explicit instructions commanding the model to synthesize an answer using only those retrieved chunks. The model functions as a data processor, tethered to the external evidence provided for that specific request. This structural boundary explains why small language models frequently outperform massive systems inside retrieval frameworks. Larger models possess such deep parametric memory that they often prioritize internal patterns over the provided context. Smaller models, with less entrenched internal knowledge, adhere more precisely to the retrieved snippets. Retrieval solves textual facts, but the model still lacks computational agency. It cannot execute precise math or query a live database. To bridge that gap, engineers use tool calling. Models are fine-tuned to recognize when they lack internal capability. Instead of guessing a calculation, the generation process halts, and the model emits a structured request to an external tool. A dedicated calculator or API performs the exact operation, then feeds the result back to the language model, which synthesizes it into the final natural language response. An isolated language model is effectively an unpredictable text predictor, but when wrapped inside a retrieval framework and given access to external tools, it becomes a deterministic, highly reliable reasoning engine. In an enterprise deployment, the system requires continuous updates to understand internal company jargon. But fully retraining the network on specific vocabulary causes catastrophic forgetting, destroying the model's broader capabilities. With QLoRA, engineers attach a pair of tiny, low-rank matrices alongside the original weights. To save memory, the massive base network is quantized to 4-bit precision and frozen. Only these tiny adapter matrices update during training, absorbing new terminology while protecting the foundational logic. Once the weights are locked, the focus shifts to production metrics. Accuracy is a baseline requirement, but the physical performance of the system under load must be rigorously evaluated. The first critical metric is latency. Engineers measure the strict millisecond delay from an incoming request to the appearance of the very first token, a calculation heavily dependent on the efficiency FNC Vcache. Next is throughput and token efficiency. This involves tracking concurrent users, optimizing batch sizes across the GPU, and calculating the pure compute cost generated by redundant prompt tokens. Mastering LLMs requires moving beyond the search for a single, all-encompassing algorithm. Success comes from engineering a continuous, highly constrained pipeline of routing, alignment, and retrieval.